I'd like to keep this door locked today.
Oh, it's scary. Don't look at it. Don't look at it, bro. I looked at the review and I said, okay. But it's okay.
Oh, perfect timing, yep. Sorry, there might be people coming in if you don't mind.
Literally 1 second.
All right, you're good. It's already locked, yeah, it's good. Okay, we have a little bit of administrative stuff to take care of first. So I went through and I was looking at the grades in the class. And this doesn't have anyone's names, so what you see here on the left column here is all the students in the class. This is average overall grade in the class, highest to lowest. And then the bottom is averages. So right now, and I've made some adjustments. I dropped your lowest quiz, and then that survey you did, I put in as a quiz grade, blah, blah, blah. So the grades should be pretty current. The 5-point bonus for the series, I already did all that. You know, the series problems, I included that. So the class average right now is an 84, right? That's the class average. These are the exam grades. Exam 1, the class average was 86. Exam 2, 77. Exam 3, 85. All very decent averages on these tests. And then the next column is what each student would need on the final to get an A, a B, or a C in the class. So like, for example, I'm just picking someone randomly here. This student has an 89.73, needs to get a 90 on the final for an A, 90.9, right? That makes sense. Going into the final with an A, with a 90, you need to keep that 90, right? In order to get a B in the class, you need a 49. And in order to pass the class, you need a 7, right? So you can probably figure out who you are in this, right? You can probably figure out who you are. If it's blacked out, that just means that that's not mathematically possible for you anymore to get those grades. So you can see everybody in the class can still pass. And there's only a small group that would need to get like a really, really high grade on the final to pass, right? So I'm bringing this up because there's been discussion about whether or not I should maybe allow your final to replace your lowest grade. And because I've done that in the past, like for Cal 1, things like that. The issue I have with that is that for Cal 2, your final exam is not comprehensive. It's only covering Chapter 8. So I have a problem with replacing a lowest exam with something that doesn't assess what you did before that you didn't do well on. So given the current state of affairs in the class, I'm not replacing anything. So I think that the class average is a mid-B, and so most students everybody can still pass the class. It's not mathematically impossible. You just have to, some of you have to do kind of okay on the final. Remember I was telling you the final exam, this is where I can't give y'all a good assessment of how hard it is, because students will see this number here or this number here and they'll say, oh, okay, I just need like a 50. And I'll have people literally come in and they'll do like half the problems and walk out because they're like, okay, I think I got those half right. And yeah, I'm never gonna get a 92, so I'm just gonna shoot for a 50. So it's hard, it skews the true difficulty of what the test is, all right? Any questions? Yes?
Would there be a way that we can retake earlier tests to show that we learned from our mistakes or something?
Well, then, okay, so that, I'm trying to be careful here. If you want to go retake a test to show you've learned, great. It's not going to impact your grade. If you want to do that just for your own, I'll be happy to make a test that you can do. But part of this is that, part of college is that you need to be ready when the test comes, right? And there's a problem we deal with a lot right now, especially after COVID, with the incoming like high school students come in. It's like they come in, they take a test. First thing they ask is, when's the retake? You know, it's like, what retake are you talking about? Well, the retake I did in high school the whole time I was in high school, right? So trying to kind of wean students off this idea that there's going to be something that's going to somehow fix the fact that you weren't ready the day of the test, right? And so in Cal 2, that needs to be something that you are like really leaning towards. Like there's no makeups, you know? So now if I had a student, you know, who had like a really good grade on the final and had one bad test, I might be open to something. But the problem with that is whatever I offer to one student, I have to offer to every student, right? So then you get into this issue of like, do I really want to make a test for everyone again that I get to make and then grade and then, you know what I mean? Yes?
I have kind of like an obnoxious question, but for like rounding, I'm not talking about like a humongous like, you know, but if we're like within a point of like an 89 to an A, what would I guess be your, how would you handle that?
On paper, 89.4 is a B, 89.5 is an A. 89.45, I mean, how far do you want to go decimal-wise, right? But I'm saying like, that's 84, that's on paper. Now, if it comes to that, right, here, the issue I have is this. If I round, I have to round everybody, right? The same amount. So let's say you're 2 points away. Let's say you have an 88, and you send me that email at the end of the semester, and you're like, hey, I'm 2 points away from an A, right? Everybody gets that 2-point curve, right? So now the person who is an 86 is at an 88, and they email me and say, hey, I'm 2 points away now. That's how it works. I promise you, I've been doing this for 20 years. And so what happens, everybody's grade gets skewed over, and then the people who are like 0.2 away are asking for the 0.2 after I just gave them 2. You know what I mean? So like at what point does it stop? It never does. So.
Can we add in like a B plus?
What's that?
Can we add in like a B plus?
What do you mean?
Like a 3.5 instead of a 3.0?
Well, I can't change the way that they do.
Is that's the university?
That's the college. That's most universities. Some universities have minus, you know, like A minus, A plus. I wish they did that. I really wish they did that. I wish they just took your numerical grade. Although that would hurt a lot of people as well because, you know, a 70 right now is the same as a 79.4. So, you know, that's not my decision, you know, that's just the way it is. So that's like a student who gets 101 average is going to get the same exact result on their transcript as a person who gets an 89.7. These two students are indistinguishable in terms of a transcript. Yeah, it's, you know, again, it's the system that I didn't make, and that's the system that we operate in. So, okay. Yes.
All right, a hard-hitting question. So does this mean, now that you've unleashed this, that you will probably not have any more quizzes? I suspect.
We might have another quiz. It's not, I mean, it's not, we still have this week and next week, right? So, I mean, it's not impossible for us to have another one. It's not high on my list of things to want to do, but.
When is the final? I know it's written.
I think it's on Tuesday. I had the schedule up earlier because I wanted to know myself.
Tuesday, is it?
Tuesday, no. Hold on. It's on Tuesday, May 9th. So look at today. Today is the April 25th, right? April 25th is today. We are supposed to be finishing 8.6. We are finishing 8.4, starting 8.5. Okay, I'm supposed to spend 2 days in 8.5, and I'm not going to be able to. I'm supposed to spend 2 days in 8.6. So this is not a reflection on you as a class, but this is the furthest behind I've ever been in the Cal 2. I've never not finished chapter 8. I've never not finished it. A lot of times I can't get to chapter 9, that's okay. But chapter 8, I almost always finish. I have never not finished. This would be a first. So that's why I said last class, we need to like, enough with the, you know, if you have a question, jot it down, get with me afterward. So let's stop talking. We've eaten 10 minutes. Are you all ready to go? If you have further questions about things, get with me, right? Okay. So we have today, Thursday, next Tuesday, next Thursday. That's it, 4 class meetings. All right, we're finishing 8.4. We did the ratio test to end class. I posted the videos yesterday. All the videos, I was backed up a little bit on videos. They should all be up to date, except when we had the incident occur, I just decided to just not include that video. So there's a time it'll skip and then, you know. All right, so now we are going to move on to the root test. This can be really quick and simple. This root test is not used very often. This is the last test on our list of tests. This test is something you want to use when you see something raised to the power of n. So it says here if we're given any series, right, doesn't matter what the series is, it can be positive terms, negative terms, whatever, that this series will converge if when you take the nth root of the absolute value of the sequence, take that limit, if that's less than 1, we've got convergence. If it's greater than 1, we've got divergence, and if it equals 1, the test fails. So it's just like the ratio test in terms of greater than 1 diverge, less than 1 converge. It's just what we're doing is different. We're not doing a ratio. So let's just do an example. This is on your, where is it on your sheet? Is it the last one, second to last one? Third to last one? 20th to last one? All right, there we go. Here's a series, right? Everyone see that all right? Make it a little bigger. Does this converge or diverge? All right, so I see this nth power here, right? And so the root test says that what I can do is take the limit. I can take the limit as n goes to infinity of the nth root of whatever I see there. So I have 3n plus 1 over 4n plus 3 all to the n. And see, the great thing about that is that the nth root of something to the nth power, those go away, right? And so you just have that and that go away. So you get limit, n goes to infinity of 3n plus 1 over 4n plus 3. All right, and now you're back to just L'Hopital, right? Infinity over infinity. Do L'Hopital one time, you get 3/4, right? And 3/4 is less than 1, and so it converges. By the way, I was supposed to do the absolute value of this, but this is always positive numbers, which is why I didn't do the absolute value. This always gives me positive numbers. So it converges. Make sense? Pretty nice, right? If you have something to the end, you can do that. All right, let's try that one. So I want to kind of show you something real quick before we do this problem. If you have 1 plus 1 over n to the n squared, that is the same as 1 plus 1 over n to the n all to the n. Because when you take something and raise it to a power and then raise all of that to a power, you multiply these powers, right? And n times n is n squared, which is where this is coming from. So it's important, I guess, for us to see this. And then let's apply the root test. So I take the limit as n goes to infinity of the nth root of the absolute value of that. Is this ever negative? No, right? 1 over n is always positive, plus 1 always positive. This is always positive, right? So I don't need an absolute value. And I'm doing 1 plus 1 over n to the n to the n. And when I do that nth root, it kills off one of the n's, right? Just one of these. And so now we're left with the limit as n goes to infinity of 1 plus 1 over n to the n. And we talked about that last class, didn't we?
Yeah, it's that
That's E,
yeah.
right? That's E. Okay, so this is E without us showing any work. And E is approximately 2.7, so that's bigger than 1. So what do we have here? Divergence. Yes?
Are we doing this process twice?
What do you mean?
Get rid of the n to the...
Nope. Nope. No, we did this to get this, and then this we know from last class and from Cal 1 that this is actually, if you do this limit, that actually turns out to be E. Okay, that's it. Root test, done. We're done with 8.4. All the tests are over, all right? You have all the tests, and now we move on to a new concept. So we're now going to talk about something called power series. So where are we? What we've established so far are these tests, right? We have these tests, and we can determine convergence or divergence with those tests. We're now going to define a new type of series, a brand new type. Pay close attention to the fact that the new series that I'm about to define contain a variable in them, x. All the series that we've had, right, have been n's, sum, n equals 1, blah, blah, blah. It's been n's and n's and n's. Now we're going to see x's in there with the n's. So let me define a power series. A power series is a series of this form. Sum n equals what? 0, starting at 0, not at 1. 0 to infinity, c sub n, x to the n. So this c sub n is actually what the a sub n used to be. Remember a sub n was like the formula that generated all the numbers? All we're doing is changing the a to a c, all right? It's like a dummy variable. So c sub n, this is just numbers. Each one of these, when you plug in a different value of n, you get a different number here, different number, different number. And then next to it, you have x being raised to just increasing powers. So when you plug in 0, what happens when you plug in 0? You get c sub 0, right? X to what power? 0. Next to the 0 is 1, right? So I don't need to put it there. And then I do 1 here, c sub 1, x to the first power, c sub 2, x squared, c sub 3, x cubed, right? So do y'all see it's just a bunch of numbers in front of higher and higher powers of x. That is called a power series because it is a bunch of powers of x, right? That's power series. So I just said here, c sub n is the formula that gives you the coefficients of the series, right? These coefficients are like the list of numbers that we used to get in a sequence, right? But now they're just the coefficients of the powers. X is the variable. This is what we would refer to as an infinite polynomial. Remember polynomial functions like x squared plus x plus 1, that's a polynomial. X cubed. Usually with polynomials, you have like what we call the degree of the polynomial, which is the highest power of x, right? Well, here it's an infinite polynomial, which means it's a polynomial where the highest power of x is actually infinite. It just keeps going. That is a power series. So what's different here? Obviously, we have a variable in there now, right? Take the variable out, and that's everything we've been doing, right? If you take the variable out, we can usually determine convergence or divergence, right? If you take the variable out. But now that we have the variable in there, that variable is going to impact whether or not the thing converges or diverges. Like that x matters, right? So the convergence or divergence of the series may, not always, but usually, depends on the value of x that we're putting in there. Yes?
Does this change the effectiveness of any of the rules we learned?
No, it's just we have to pay attention to x now. We have to take the x into account. So now that we've defined a power series, here it is, right? Since it has a variable x in it, we can now define a function. We can say, hey, look, since this has x's in it, and I can change the value of x, then I can look at this power series as a function of x. All right? So if I say, hey, what's f of 2? Then what I'm doing is I'm replacing all these x's with 2's, right? If I say, hey, what's f of 3? Then I'm replacing all the x's with 3's. If I say, hey, what's f of 1? You replace all the x's with 1, right? So you can define a function that way. But the thing is, there are certain values of x that when I plug them in, I might get convergence. And there are other values of x that I plug in where I might get divergence. Does that make sense to you? If I change the value of x, that's going to possibly change the convergence or divergence of the series, because for each different value of x, I have a different series. Yeah? So this function only makes sense, right? The function only makes sense if it converges. Like if I plug in a value of x and I get divergence, then I don't get an output. Let me give you a basic example. Let's say I gave you this function, f of x equals, let's go back to college algebra, 2x plus 1, right? If I ask you to start plugging values in for this, you can give me outputs, right? Plug in 2, you get 5. Plug in 3, you get 7, blah, 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 right? So there's nothing I can't plug into this. I'm going to get an answer, right? Where if I give you something like this, I can't plug 0 in, can I? And I can't plug negatives in, right? So this function is only defined for positive numbers. This function is defined everywhere. So we would say the domain of this is everything, right? And the domain of this is all values of x greater than 0. If we're defining a function now to be an infinite power series, there are some values of x that work, convergence, some values that don't work, divergence. And thus, the values where it does converge would be in the domain of the function, whereas things that make it diverge would be outside of the domain. Just like over here, right? We have a domain. Here, the domain is everything. Here, domain is all positive numbers. Our question is going to be, for what values of x does this thing converge? All right, so a first example, right? We need our first example of a power series, and here it is. I'm going to write over here off camera the definition of power series. We have f of x equals sum n equals 0 to infinity, c sub n x to the n, which is c sub 0 plus c sub 1 x plus c sub 2 x squared plus c sub 3 x cubed, and so on and so forth. That's a power series, right? Now, that c sub n out front can be any formula you want it to be. It can be anything, right? Just like the a sub n used to be all sorts of different crazy things. So for our first example, what I'd like to do is I'd like to define my c sub n to be very boring. It's just always the number 1, no matter what. So that means c sub 0 is 1, c sub 1 is 1, c sub 2 is 1, c sub 3 is 1. They're all 1s, right? And doesn't it turn it into this? Right? It's just 1 by itself, then 1 in front of x, then 1 in front of x squared, 1 in front of x cubed. Boring, boring, right? And that turns into this, yes? That is your first example, specific example of a power series. This looks familiar, should look familiar to us. I want you to go back and think about the geometric series. Remember the geometric series? And I said there were 2 different ways to write the geometric series. One way, I'll do it off camera, one way was like this, where we started the index at 1. That was the formula for geometric series when we started the index at 1. But I said if you shift the index to 0, then you don't use r to the n and n minus 1 anymore, you use r to the n. Do you remember me showing you that? So this is the second version of the geometric series. If we write this out, starting with n equals 0, we get this, right? Do y'all see that these are almost the same? If I replaced all my a's with 1s, what would I have here? 1 plus 1r plus 1r squared plus 1r cubed, right? So they're gone. And so it would be like that, except instead of r, we have what? X. Do y'all see that? That example, right? This is the generic power series. If c sub n is defined to be 1, then we get that power series, which is a geometric power series. And it will converge when? Well, when would this converge? What's the condition in geometric for convergence?
The absolute value is greater.
Less than. We need the absolute value of r to be less than 1, right? So for that up there to converge, what do we need to happen?
Absolute value of x.
Absolute value of x has to be less than 1. All right, so that's the next note here. So I say if we replace the a's with 1s here, and we think, okay, all the r's are really x's, then it's the same, this is a geometric series, and just like we said the absolute value of r had to be less than 1 for convergence, with this series, the case is that the absolute value of x has to be less than 1. Okay? Therefore, what we could say is that if we define a function to be that series, then the domain of it is all numbers between -1 and 1. Further, if it converges, what does it converge to? Do you remember what a geometric series converges to? If it converges, what does this converge to?
A over 1 minus R?
A over 1 minus R. And for us, A is what? In this, what's A? 1, right? So if this converges, right? If this converges, if that converges, right? Then it will converge to A, but A for us is 1, you said?
Yeah.
Over 1 minus, and R is really what for us? X.
Yeah.
It'll converge to that.
So we can find so to find what it converges to, we can do it for power series, geometric, and telescopic? Or is it just still geometric and telescopic?
Well, it depends. See, this is a power series, so we have that X in there, right? It's a little... Geometric, telescopic are not power series because they don't have an X in them. We can tell what they converge to. If they converge, we can tell what they converge to. But as soon as we put an X in there, it changes the game. Completely changes, because then we have to pay attention to the X, and it could change the convergence or divergence. This is just a first example of a power series, very first example. So let me recap again, because this is there's a big takeaway that I'm about to state. It's going to be subtle, but it's so important. What we're saying is this, that 1 plus x squared plus x cubed plus x to the fourth forever, all of that written out forever, is equal to that if the absolute value of x is absolute value of x is less than 1. So that means give me a number between here and here, 1/2, right? If I plug in, if I do on my calculator 1 plus 1/2 plus 1/2 squared plus 1/2 cubed plus blah 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 blah, if I did that forever, it would be the same as plugging 1/2 into this. If I took the number 2 and plugged in there, it would diverge and I wouldn't even look at this anymore. If I took a number like 7/8, 7/8 is in here, right? 1 plus 7/8 plus 7/8 squared, blah, 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 forever is the same as plugging 7/8 into this. Okay? All right. Yes, yes? So what I'm going to do now, this is, to me, this is awesome. I don't know if you're going to like this. You'll like it. Okay, I'm going to have the computer graph this function. Do you all agree I could go to Desmos and graph that? Okay, I'm going to have my computer graph it. And then what I'm going to have my computer do is start to try and graph this, which is impossible for my computer to do because I can't go forever, right? So what I'm going to do is first have my computer graph 1. Do you all know what the 1 function looks like? Like this. Then I'm going to have it do 1 plus x. What would 1 plus x be? It would be a slope like this, but moved up 1. I'm going to have it graph that. Then I'm going to have it do 1 plus x squared, which should look like a parabola. And then I'm going to have it do 1 plus x squared plus x cubed, and that's going to look like a cubic polynomial, right? The further out I go, the more the graph should look like this, but only between -1 and 1. Watch, this is awesome. Let's see if I can fit this on here. All right, so what you're seeing right now in red is the graph of 1 over 1 minus x. That's the red graph, okay? See it? And then I've shaded out here and here because that's between -1 and 1, right? So I want you to only focus your attention in this whitish area in here. And the black curve that you see is the power series. Right now I've only graphed the first term of the power series, which is 1, right? Is the black a good approximation of the red? No, that sucks. Right? So what I'm going to do now is I'm going to go to the next one, 1 plus x. 1 plus x, is that a little bit better representation of the red? Better, but not very good. Okay, 1 plus x squared. Is that better? It's getting better. 1 plus x cubed. Better?
Better.
1 plus x cubed plus x to the 4th, to the 5th, to the 6th, 7th, 8th, 9th, 10th, 11th, 12th, 13th, 14th, 15th, 16th, 17th, 18th. See what's happening? You don't? Right? What's happening? The further I go out, it's like the black curve is finding its way on, like, to fit right on top of the red curve. Now, over here, it's really, I mean, in here, it's really good. I've got some problems over here, and over here, I've got some problems, right? But I've only gone 33 terms out. How many terms do I need to go still? Forever. And the idea is that if I could go forever, they would be the same functions. All right? That's what? Do you mind opening? I'm sorry. So look, I know that people are going to be like, well, wait a minute, hold on a second. Like, why would you ever want to deal with this as opposed to that, right? Like, that's a much easier function to work with, right? Plug 1/2 into that, it's much easier than plugging 1/2 into that. I agree. I agree. It's much easier. However, the idea here is that this will work for any function, not just this one. So like any function that you've ever worked with in your life has a power series, every one of them. And you know, in this class we had some trouble finding derivatives and antiderivatives. Sometimes, but not in this class, derivatives weren't so bad, but antiderivatives, you know how we struggle with antiderivatives? What if we had something where we were trying to find the antiderivative, we couldn't do it, but I told you that that function had a power series? What if I told you that? Then do you agree that whatever its power series was, all it would be was a bunch of numbers in front of powers of x, right? Yeah. Not this series. This power series is for that function, but for other functions, there's different power series. If I asked you to differentiate this, could you? Could you take derivative of that? That? Could you integrate it? Could you integrate that? You could do it term by term, couldn't you? And it would be easy, because power rule's easy, right? Power rule's easy. So the idea for the implications of this are that any function that we ever get, if we can turn it into its power series, integration and differentiation become simple. Now, we have to stop at some point, right? Because we can't go forever into the power series. We've run out of lifetime, right? But, so you'd argue, well, then it's useless because we can't go forever. But in the real world, we can only manufacture things within certain tolerances, right? So if we go far enough, we're close enough, right? So maybe you're like, okay, look, no, you're too far off. I'll say, okay, how far do you want me to be off? I'll get there. Just, you know, do I need to go 100 terms out? I'll go 100 terms out. And so for all practical purposes, power series is like the ultimate weapon for integration differentiation. That's why when you go to like Wolfram Alpha and you ask it to do an indefinite integral, right? Let's have it do it, man. I want to spend so much time in this and I can't. No, like let's do this one. Let's do let's try to find the antiderivative of e